Okay, to start with, our transverse wave, which will be our quadrature motion, be represented by this form. As we can see, I have an exact analogy to what's drawn on the board. If I transmit just one pulse, you can kind of see it takes a long time to get to the other end. But the longitudinal wave, of course, is over there almost immediately, and other than the slippage at the other end, it's almost undetectable that this wave even exists, other than that little shaking around. But it's slower. There we go. See, there's really not much motion up and down or around, but it's there right away. As soon as I move my hand, the other end responds, where in this case it takes a very long time to get there. So this serves as a very practical analogy of these two types of waves. Okay, as to carry our analogy further here, if we drop a stone in the water, we'll produce both types of waveforms in the water. Now we know the transverse waves form concentric rings which propagate out. But the longitudinal waves, which are not normally seen, of course, travel as straight lines in the depths of the water, which are indicated by down this way. Now this also happens to be the electric field around one wire, or what's called electrical conductor. Now if we look over in the other page here, we see when we start having a system of conductors, then the field changes, and we can have either the transverse motion of electrical energy, which moves into the paper, or in other words in the directions of the wires, which these are being the cross sections of the wires, or in a transformer, energy is conveyed longitudinally from primary to secondary conductors. So we have again our two types of fields here, representing longitudinal and the transverse, which of course is hard to represent because it goes into the paper. And again, these things are at right angles to each other. The longitudinal is going that way and the transverse is going this way.